morning, students. Hope everyone all are safe in your home, and I expect everyone write assessment exams will be prepared for next assessment exams. Okay. So coming to last class, we discussed related to chapter 7, that is idea of algorithmic efficiency. We calculate here computational complexity here. So when we discuss about the concept of computational complexity by using different algorithms, already we discussed previous classes. Okay, so calculate to find the whether the given number is prime or not in two techniques. One is prime number definition technique, that is linear search, okay, linear technique. Second one is by using root n approach. Which one is the best one? In first technique, the order of n is equal to n. In second technique, the order of n is equal to root n. So which one is the least among these two order of n? So root n is less than n. That's why second technique is the best one. We decided already in previous class. In the next class, last class, we discussed. Okay. So in a given, they give. Okay. In the given problem, they are given list of elements. Okay. We find one key search element from the given list of elements by using the linear search technique. In linear search technique, we compare every element, okay, with the key element. In this way, we proceed, okay, while loop in that technique. Okay, so we decide finally n is the order of n in that by linear search technique. Why? Because we take, when we calculate computational complexity, we consider only dominant term, that is order of n. Okay, remaining constants we consider as negligible. Okay, all the constants are summation, then all the constant summation is equal to constants. That way we neglect that. Okay, negligible, that constant value. Then we finally take the dominant term. So in that linear search technique, dominant term is n. That's why. So the order of n, when we consider searching an element in an array by using linear search technique, is n. Today we discuss and we calculate here the time complexity or computation complexity of the same problem, that is given array, by using different technique, that is binary search technique. Then what is meant by binary search? What is meant by binary search? So binary search means you already learn. So you know very well dictionary, English dictionary. When we are searching, best example for binary search technique is searching for a word in a English dictionary. For example, we search one keyword, okay, in the dictionary. We first divide the, suppose we are searching for read keyword. First, we entire dictionary can be divided into two parts. So first time when we searching, okay, we not start with capital letter A. We middle of the, first we divide the middle. Then middle, suppose K is there in that middle page having words K. So we compare K with R. Why? Because we are searching the keyword read. Read start, the letter starts with R. First we compare K and R. Here K is middle element. Middle. Why? Because we divide the entire big problem into smaller set of subproblems, two subproblems. So entire searching can be divided into two subproblems. We search middle element with the key element. So if the key element is greater than middle element, then we search the, okay, so suppose we start searching, suppose starting A to Z, dictionary, this one is dictionary, okay, in this dictionary, okay, so we calculate read, we search for an element, for an keyword, that is read in dictionary. So first we divide the dictionary. Here this one considered as low, this one is considered as high boundary. We set the two boundaries here. First one is low, second one is high. Then we divide the entire big problem into two subproblems. This one is one subproblem, this one is one subproblem. So the entire problem in binary search technique divides into two subproblems. This one is one subproblem, this one is one subproblem. See here in this subproblem, okay, we first, this one is K, okay, kill keyword here is there, K. So we compare this K with R, K with R. So R is greater than K, that's why we search. So all these words are below K, A to K words. These are above K to Z elements. Then we search process in this second segment. So the entire segment can be divided into two smallest segments, and we set, okay, this one is one segment and this one is another segment. Then we search the process in this. So we first calculate, divide the entire big problem into two subproblems, and then we set the mid element. This one is mid element. Then we search, our keyword is both are same or not. If both are same, we search, our search process is start. Otherwise, so if the key element is greater than this middle element, that's why we search the read word in the second segment. Okay, suppose if the read key search element is less than this middle element, then we search process in the first segment. In this way we decide. According to mid element, basing on mid element, we decide, we process the technique, binary search technique. Okay, we search the element in this segment or in this segment. Basing on that, we decide. Okay, so next, so mid element, here we calculate mid element basing on mid element position. Basing on mid element position, okay, we compare key element with AR of mid. Suppose if less than is greater than, then we decide this search process continues in this segment or in this segment. Suppose here we search this segment, okay, read. Then we set here, so this problem, we reduce our problem size here. Then here we set the lowest element. This can be already set to high. Here in this case, okay, our problem size already set to high, but low changed. Okay, change it to already here mid element, mid plus 1. Mid plus 1 is, see here, low is equal to mid plus 1. In this way, we set a low and high. Then again we search we apply the binary search technique in this segment. Then we again divide the entire this segment into two parts. Okay, so this one is smallest part, this one is also smallest part. We calculate here mid term. Then we compare the mid with our key search element. Okay, compare these two. If mid is equal to key search element, our search starts. Okay, search element is found. Otherwise, if key search element is less than, okay, key search element is less than the mid element, then we search the process in this segment. Okay, in this segment. Okay, if it is greater than mid element, our key search element is greater than this mid element, then we search the process in this segment. In this way, we continue every time. Okay, we divide in this process in binary sets, the entire problem can be divided into smallest set of two subproblems. Then again, let's take either one of the subsets and same technique applied in that subset. Okay, in this way we divide number of times until we reach key element. Otherwise, if the key element is not found, then we display the none. That means our key set element is not found in the list. We display that message. In this way we proceed. Okay, this technique. See here, I am taking one example. Okay, for doing this. So the best example for binary search technique is searching an element in a dictionary. Already we discussed here. Next, I am taking one list of elements. Okay, numbers, and search all the elements one by one. Key search element I am taking and search that key search element is present or not. So I am taking here one list or one array. See here, I am taking one array. I am taking one array. One, two, three, four, five, six. Here, 6 elements. So 5 elements I am taking. 5 elements are there. See, this one is 23. This one is 32. This one is 5. This one is 8. This one is 72. So I am taking 5 elements in the given array. So those 5 elements are 23, 32, 5, 8, 72. Okay. See here, I am starting my search from this one is first we set. Okay. So first we calculate length of array. Length of array. Here length of array is equal to 5. Length of array is equal to 5. So here we start with 0 to 4. That's why, okay, that's why total 1, 2, 3, 4 plus 1. That is 5 elements. Here, okay, length of array. Then we set low. Low is equal to the position. Here, low position is 0. High position is 4. High position is 4. So low is equal to 0. High is equal to length of array. That means 5 minus 1. High is equal to length of array. Okay. Length of array minus 1. Here length of array is equal to 5 minus 1. 4. So the position of the array, the index, this is calling it as index. This is calling it as index or position or location of the array element. Okay, set to here, low is set to 0, high is set to 4. Our key set element is 8. Our key set element is 8. We start the search starting from the given problem. See, low is set to 0, here high is set to 4. High, how high set? High here, length of array minus 1. Here length of array is equal to 5 minus 1, 4. Then we start the search process. We begin the search process. Okay, first we search low and high, then we calculate mid. So here, okay, so first we check low is less than or equal to high or not. This one. This condition we check. Low is less than or equal to high or not. See here, low is less than or equal to less than high. That's why 0 is less than 4. This one is true. Then we go for midterm. So first we check here, low is less than high or not. Okay, this one is true. Then we calculate mid is equal to midterm. Mid is equal to low plus high divided by 2. Low plus high. So 0 plus 4. 4 divided by 2. 2. So low plus high. 0 plus 4 by 2. That is equal to 4 by 2. That is equal to 2. So we calculate if it returns decimal value. We take only integer value. But here it takes only mid value. Okay, it only integer value. That's why we take mid is equal to 2. See here, mid is equal to 2. Okay, so then we set the middle element is 2. So that's why mid element is 2. Mid position is 2. These are the positions 0 to 1, 2, 3, 4. These are all positions of the elements, index or location. Okay, so then we set the mid position 2. So that's why we divide the entire array, okay, list of elements into two parts. Okay, yes, two parts. Then we find the key element. Then AR of mid is equal to 5. Then we compare 5 with then we compare. So the tooth element, array of two element is 5. Then we compare. Our key set element is 8. Our key set element is 8. Our mid element is 2. Then compare. Our mid element is 5 here. Okay. Our mid element is 2 position, mid element is 5 here. Compare 5 with 8. So key element is greater than ARR of array of mid. AR of mid. So if key is equal to AR of mid, then print return mid. Mid is the your key set element and display that position and element where it is located in the given set. Okay, in the list. Next, suppose if the key is not equal to array of, if the key element is not equal to array of mid value, okay, so here in this case the key set element is not equal to array of mid value, then we go for, then we search key is less than, okay, key is less than array of mid or key is greater than array of mid. Here in this case on our example, okay, so key element, mid element, so key element is above the array of mid. That's why we go for search in this list. So the entire problem can be divided into, okay, 3 parts. Actually 2 segments here, 1 mid element. We already checked with mid element. This mid element, if the mid element is, okay, is our key set element, then display that position and the location of the key set element. Suppose here this entire set can be divided basing on this mid element 2 parts. Then we continue the search in this list or in this list. We compare if mid element, key element is less than this array of mid element, we continue the searches in this problem. Otherwise, we continue this search process in this second, okay, in the second list. So in our example, we continue the process in second list. So then we set in this case our problem reduces into 2 sub problems. So one is this set, one is this set. Then we set here also low and high. Then we consider searching in this segment. When we consider searching in this segment, we set the low and high. High already not changed. Why? Because here high is always this one. Here we can change the low value. Set the low value. This one is mid element. So mid plus 1. Mid plus 1 is low here. See, then we set the low mid plus 1. If key element is greater than array of mid, okay, so greater than array of mid, low is set to mid plus 1. If key element is less than array of mid, then we already set to low here, set to low, then we set the high here. Okay, so in this case we set high, in this case we set low. So depends on the mid value position and compare this key element with mid element, we decide such process is continued in this section or part or in this block. We decide. Depends on this. We set the, here we already set low. No need to set low. We set here high. Here high is equal to, how to set? Mid minus 1. Here high set to mid minus 1. Here low set to, here already high set. Low set to mid plus 1. In this way, we set in this case high, in this case low. Here already low set, here already high set. In this case we set high, in this case we set low, low. So again same process. Okay, suppose we search the key element 8. So that's why we take here our big problem can be divided into only this time. Okay, these are not, we are not consider these elements. In this case we consider only these two elements, 8 and 72. Then we set high and low here. Here, okay, high is this one. So 0, 1, 2, 3, 4. So high is equal to 4. Okay, low is equal to this one, 3. Then again we divide the key set element to two parts. Then we calculate the mid. We take integer part. Then we compare 8 with 8. This one is mid. High plus low. High plus low by 2. Okay, high plus low. So mid is equal to high plus low by 2. 7 by 2. 3.5. We consider only integer part. Okay, when we have any points, we take only integer part. So third, this one is. So our mid value is equal to set to 3. Area of mid is equal to 8. Then we compare key element with area of mid. Okay. So both are same. Then our key set element is formed. In this way, we continue our search process until we reach to one element. That one element is our key search element. In this way, we continue the loop every time when we are searching. Okay, the loop divided into two parts. So n by 2. So our key search element divides. N elements can be divided into n by 2. How many times repeated? Suppose k times. So n by 2 power k. N by 2 power k is equal to, then when you reach our key set element is one element. That's why n by 2 power k is equal to 1. In this way we proceed the time complexity of this algorithm. So how to calculate the time complexity of this algorithm. See here, so when we consider binary search algorithm, we require one list of elements array, that is AR. Okay, one list of one key search element, key. AR means array. Already we are taking here list of elements array. Key search element key. Here first we set low. I am taking 5 elements. Okay, 1, 2, 3, 4. Okay, 5. So this one is set to low, this one is set to high. So low is equal to 0. So this one is 0, 1, 2, 3, 4. High is equal to, how to assign high? So total elements 5 minus 1, 4. That's why here length of array. Total elements means length of array minus 1. In this way we set high here. Okay, we set low is equal to 0, high is equal to length of array minus 1. Then we search process starts. Our search process starts here. So see here, we compare these two first. Okay, low is less than length of array minus 1 here. Then low is less than high. Then we continue the search process. In this way we search, continue, we divide the entire all the n elements into n by 2 parts. Okay, so we calculate mid value. Mid is equal to low plus high divided by 2, and we consider if it is having any decimal values, we consider only integer part. So integer of low plus high by 2. Okay, so then we search the key element with mid value. So if key is equal to array of mid. See here, mid, high, low, these are all positions of the elements, index. Here, if key is equal to array of mid, if key is equal to array of mid, okay, so then our key ch element is found in the position, mid position, and return the value of mid. Suppose if the key element is less than, okay, array of mid, then we search the process. This one is mid, low plus high by 2. So then we search the process in this list or in this list. The entire set can be divided into two parts. One is this one is this one. We search the element in this list. Okay, or we search the element in this list, because already we search the element, this element. If it is okay, is equal to key element, then we return this mid element. Otherwise, we decide search, the given search, continue in this search or in this list. So further we write here, if else if key is less than, we compare mid element with key less than or greater than. If less than, we process, search process in key is less than. Okay, is array of mid, then we process this element and set. Already here low is set. Then we set the high. High is set to length of array minus 1. Always high is set to length of array minus 1. Okay, here only two elements are there. Only two elements are there. So 2 minus 1, 1. So this one is set to high. When we search the process in this list. Suppose when we search the process in this list, so here already low is set, then we set the high. In this process we set low. Okay, we set already high here, so low. Here in this low is equal to, already this one is mid element, mid plus 1, mid plus 1. So this one is mid plus 1 is low, already high is there. So low plus high by 2, calculate mid. In this way, every time we divide the entire given list of arrays into n by 2 parts. So here n by 2 is important. How many times? N by 2 divide the, okay, n by 2 times. K times it repeats this loop. This loop repeats k times, for example. Okay, each and every time divide the size of list of elements into n by 2. That's why, so n by 2 into k. So we assign the time complexities and finally we calculate the order of n by using this technique. See here, this one is set to constant time. When we calculate, we assign constant times for every statement in the program. So here this one is C0. I am set to this one C0. This one is time constant time C1. Okay, C0, C1. Here this one is one condition. So okay, this one set to C2. Okay, this one is one calculation statement C3. This one is one comparison statement set to C4. Okay, this one is one statement C5. This one is C6. This one is C7 set to C8 set to C9. See, when we assign constant times for each and every, here this while loop continues until in this n by 2 times, n by 2, this can be divided into n by 2 into k times repeats, k times it repeats. So k times it calculates n by 2 in this process. So that's why, so here how many times while loop repeated? How many times while loop repeated? N by 2 n by 2 power k. Then we reach one element. Okay, our assumption is we calculate one key such element, that is one element. So n by 2 power k is equal to 1. That is n by 2 power k is equal to 1. This means n is equal to 1 into 2 power k. Okay, that is 2 power k. N is equal to 2 power k. So k is equal to log n to the base 2. So n is equal to 2 power k means we place here k is equal to this 2. Consider this one. Okay, log n to the base 2. So here how many times? K times. K means log n to the base 2. In this way we calculate, okay, how many times this key searching process is continued. Then we calculate the time complexity for the above problem. Okay, so then we calculate the time complexity for this problem is time complexity is equal to, okay, see, time complexity is equal to first C1 plus, so this one how many times repeated? Log n to the base 2 times. Okay, log n to the base 2 into here C2 plus C3, C2 plus C3 plus C4 plus C5 plus C6 plus C7 plus C8 plus C9. Okay, plus C9. Okay, so C9 considers last. If it is not set to any mid element is not found here. Mid element is less than, greater than. This one is last execute. That's why this one considered as C9. Okay, in this way we calculate the time complexity. Why? Because here log n to the base 2 times this while loop repeats. So this while loop consists all these statements. That's why we consider this one as C1 plus log n to the base 2, C2 plus C3 plus C4 plus C5 plus C6 plus C7 plus C8 plus C9. Okay, see, this one is constant plus constant. This one is also constant. So this one, so x plus log n to the base 2 into y, for example here, into y. See here, since x is equal to C1 plus C9, y is equal to C2 plus C3 plus C4 plus C5 plus C6 plus C7 plus C8. This one is constant. This one is also constant. So in this way we conclude that C1 plus C9 is equal to constant. This one is also constant. So yes, x and y are two constants. X plus log n to the base 2 of y. So the final we consider here dominant term. So the dominant term is n. So where in this expression n is there? Here. So that's why log n to the base 2. Log n to the base 2. So order of n for binary search algorithm is log n to the base 2. Okay, log n to the base 2. So last, okay, linear search. So binary search. Okay, order of n is equal to log n to the base 2. Linear search, order of n is equal to n. See here, log n to the base 2 is less than n. Always it less than n. That's why, okay, which is the best one among two? Binary, this one is less than. Okay, so n is greater than log n to the base 2. That's why we consider binary search technique is best technique among the two linear search and binary search techniques. So in this way we calculate for a given problem, list of number of techniques are there, then we calculate for each and every technique, we calculate the time complexity, then we decide which one is the best one among all these techniques, then we continue the process microprocessor. So this is the task of operating system. So operating system calculate this time complexity and decide which one is the best one and continue the process, the best process among all these techniques. So this is the concept today we discussed here. Next class we discuss some of the questions related to this chapter 7 topic. Thank you, students.